Okay, in section 12.4 we're going to put together our use of means and standard deviations to solve some real problems. Ultimately, most data, if it's collected with enough samples, is going to create a normal distribution. Okay? We call this normal distribution, as you can see, we call it a bell curve or a Gaussian distribution. Okay, it's going to be bell-shaped, symmetric, with a vertical line through its center. Okay, and the mean, median, and mode are all equal and located at the center of the distribution. So, if we can say that our data is normally distributed, then there's some interesting facts that come from that. Now, again, is all data normally distributed? Absolutely not. Okay, but again, we're going to go on the premise that the data that we're going to be using is going to be normally distributed for the problems that we're going to look at today. Okay. So, first of all, if we look at the shape of the bell curve, the shape of it depends on the mean and the standard deviation. Okay, these three graphs have the same mean but different standard deviations. Okay, ultimately, as standard deviation increases, okay, the distribution becomes more spread out. So when we have a larger standard deviation, it's going to be more spread out. Okay, if the data are closer together, we're going to have a curve that looks like it's closer together on the sides. Okay. Now, there's a rule that we're going to use here for normal distributions, and it's called the 68, 95, 99.7 rule. Okay, and what it boils down to is that when we set up a situation where we know a mean and we know the standard deviation, okay, we can draw a picture of this bell curve and we can make marks 1, 2, 3 to the right of the standard deviation, or of the mean, 1, 2, 3 to the left. Okay, and this represents one standard deviation to the right of the mean, which ultimately means above. This one means -1, that means below the mean, etc. And what it boils down to is if we do have this normal distribution, that approximately 68% of the data falls between one standard deviation of the mean, either left or right, or below or above, if you will. Okay, 95% of the data is going to fall within 2 standard deviations of the mean, and then 99.7% of the data is going to fall within 3 standard deviations of the mean. Okay? So let's take a look at that in action here. We have male adults in North America are approximately normally distributed with a mean of 70 and a standard deviation of 4. And we want to find the height that is 2 standard deviations above the mean. Now, if I were to draw a picture of that situation, which I certainly would want to, and anytime we have a normal distribution, we're going to want to draw a similar picture here with a bell-shaped curve. We're going to put the mean in the middle, and then we'll make marks 1, 2, 3, 1, 2, 3. You don't have to be a perfect artist or anything like that. But ultimately, if the mean of the heights of the males in North America is 70 and the standard deviation is 4, that means one standard deviation away would be the men that are 74 inches, and then 78 inches, and then 82 inches, and so on. And we're adding 4 each time. Same thing going left, we'd subtract, and we'd go that. So ultimately, if you are 78 inches tall, then you are 2 standard deviations away from the mean, which means you're in a fairly rare group. Okay? So again, the question is find the height that is 2 standard deviations above the mean. Well, of course, that's this one. That's going to be 78 inches. That's 2 standard deviations above the mean. And again, the further away you get from the mean, of course, that tells you that you're essentially more special in this case. And there's very few people that are going to be in these 2 groups as compared to that are going to be in the middle, that are between 66 and 74, etc. Okay. So if we what we want to look at next here is the same situation. We're going to use this distribution. Okay, we want to find the percentage of men in North America with heights between 66 and 74. Well, luckily for us, 66 and 74 are actually on the chart that we made here, and that means that we want to tell how many people are in this group right here. Well, again, if you remember, we had earlier our 68% rule was between -1 and +1. Okay, 1 standard deviation below, 1 standard deviation above. Okay, and we know that in between there should be 68% of the people. So therefore, the answer then is in fact 68%. Okay, had they asked us between 62 and 78, we would have said 95%. Had they asked us between 58 and 82, we would have said 99.7%. Going further, if they would have said between, let's say, 70 and 78, for instance, keep in mind, if this is 68, that means that these are 34% and 34%. Okay? And remember, if this whole thing is 95, okay, from -2 to +2, if you will, okay, if that's 95, keep in mind we've already used 68 for this part. If we do 95 minus 68, we get 27. Okay, so that means in each of these individual parts there'd be 13.5. And if you set up your table like that, now we can answer a question like how many men would be between 70 and 78. Well, it would be the 34 here and the 13.5 here. We would say it's 37.5%. Okay. And we can also do similar work to figure out how much is in this group and how much is in this group. And keep in mind in these tails, if it's 99.7 from -3 to +3, okay, that means there's only 0.3% left. So if I go 0.3 divided by 2, that's going to be 0.15. Okay, so that means that there's going to be 1.5% of people that are going to be in that group, 1.5% of people that are going to be in that group. And keep in mind that when we add up all of these percentages that we have in all 1, 2, 3, 4, 5, 6, 7, 8 different regions, okay, they had better add up to be 100. So that could tell us right now what's going to be in this group, because these two together make 15, and I did that backwards, sorry. This is 0.15%, sorry. So 0.15%, not 1.5. So you're in a pretty elite group if you're on either side of that mean. Okay. So if I did 34 plus 13.5 plus 0.15, we would end up with 47.65 on this side of the curve. Keep in mind that half the curve would be 50, the other half would also be 50. So that means it would be 2.35 in that group, okay, and 2.35 in this group. So if you have this as your in your notes, you can use it to answer lots of different questions because you already have the percentages laid out. You just need to decide which group are we after. Okay. Now, one of the things that that we generally do here to make this job easier for us is we use what we call z-scores. Okay. So if we calculate the z-score essentially just tells you how far away from the mean you are in terms of higher or lower. And ultimately we're going to take the data item, whatever it is, we're going to subtract the mean, and then we're going to divide it by the standard deviation. So in this case, if I knew that I was 74 inches tall, and I subtracted the mean and divided by the standard deviation, I'd have 4 over 4, which equals 1. And all that represents, the z-score represents how far away am I from the mean. Okay, if I'm 1 away, that means I'm exactly 1 standard deviation to the right. If it had been -1, I would have been over here, and I'd have been -1, left 1, if you will. If I had a z-score of a half, that means I'm somewhere in the middle. Okay. Now, in terms of percentages, if we're somewhere in the middle and we're not right on these nice numbers, okay, then we're going to have a difficult time figuring out what the numbers are in terms of percentages. We'll deal with that in the next section. Okay. But for right now, we're going to be on each of these different standard deviation numbers, whatever they may be. Okay. So let's look at an example here. It says the mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8. Okay, and you notice that they set up their table similar to what we did with ours, with a 7 in the middle, 7.8, 8.6, 9.4, and so on. Okay. And then ultimately it says the weights of the newborns are normally distributed. So find the z-score for a weight of 9 pounds. So again, if we do 9 minus 7 divided by 0.8, okay, we do the data, divide or subtract the mean, divide that by the standard deviation. Turns out that that particular weight is 2.5. Okay, going back to our bell curve, remember this was 2. If I'm at 2.5, okay, that puts that baby in a pretty elite group in terms of weight. And there's not very many babies in America that would be that big in this particular case. Okay. All right. Now, here's another question. It says intelligence quotients are normally distributed. The mean of 100, standard deviation of 16. And the question is, what is the IQ score that corresponds to a z-score of -1.5? Well, if it's negative, remember we're going to be less than the mean here, so we're going to go down 16. Keep in mind what get us to, if you think of your picture, if I were to go 100 here, if I went down 1 z-score, that would be 84. If I went down 2, okay, that would be 68. Okay. And if it's 1.5, it would need to be right in the middle of those two. Because again, this is -1, this would be -2. So right in the middle of those two, if I were to add those two together, 68 and 84, find the middle of those two, that would be at 68 and 84, be 152. If we divide that by 2, we're going to get 76. Okay. So 76 would be the IQ that would correspond with the negative 1.5 z-score, as shown here. Now again, what does that tell us? That means that ultimately, if you're at this point, okay, that this many people are going to be ahead of you in terms of IQ. This many people are going to be below you. And again, it's a percentage above and a percentage below. All right. The other thing that we're going to look at here is what we call percentile. Okay. It says if n% of the items in a distribution are less than a particular data item, we can say the data item is in the nth percentile of the distribution. So if I were, let's say, in this particular distribution, if we have 25% of the data in each of these groups, if I'm this person right here, okay, I would be in the 75th percentile because 75% of the data is lower than me. If I were at this person, okay, then I would be in the 25th percentile because 25% of the data is lower than me. Okay? And ultimately we call these quartiles as well. If we divide the data sets into 4 equal parts, okay, the 25th percentile is the first quartile, second quartile, which is also the median, and the third quartile, or the 75th percentile. All right, and then one other thing I want to look at here is using a z-score in a table, you can find percentage of data items that are less than any data item in the normal distribution. I mentioned that earlier. Right now, we can only deal with this situation where we land on one of the -1, +1, etc., okay, where we know the 68, 95, 99.7 rule. Okay, what we're going to learn in the next section is that it really doesn't matter, okay, whether we're on one of these or not, okay, because there's going to be a nice table that we can look at that's going to tell us the percentage, and we'll study that in the next section. Okay. All right. And one final part to this we're going to talk about in this section is margin for error. Statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening. So if we have an n sample size, there's a 95% probability that it lies within 1 over the square root of n of the true population statistic. So ultimately this right here is our formula that we're going to use for what we call margin of error. Okay, if we know how many are in the sample size, say there's 50, we do 1 over square root of 50, and we'd multiply that by 100%, and that would give us our margin for error. Okay? And notice it's plus minus because it's going to be error on one side or the other. It doesn't really matter which side, kind of going to be to both sides. So here's an example of a problem that we would do. If we have in a random sample, there's 1,172 children. 17% of the children say that getting bossed around is a bad thing about being a kid. So we want to verify the margin of error. So if we do 1 over the square root of 1172, okay, times 100%, it turns out to be plus and minus 2.9%. Okay, so that is the margin of error that we would calculate, plus and minus 2.9%. Okay, and then in part B it says write a statement about the percentage of children feeling that way. And so again we would write, and again this never changes. There's a 95% probability that the true population percentage lies between. And then we would take that 17 that they gave us and we'd subtract 2.9%, and then we would add 2.9%, so it would lie between 14.1 and 19.9. Okay. All right. And finally, we'll look at just another example of some other kinds of distributions. Okay, this graph represents a population distribution. Okay. And ultimately, what we see here is that the most frequent income, the mode, occurs toward the low end of the data items. The mode is over here. Okay, this data is called skewed because notice that it's not a nice bell-shaped curve like a normal distribution. Okay, because a large number of data items are piled at one end or the other, with a tail at the other end, and we say that this graph is skewed to the right. Okay, so wherever the tail is, if you will, is where it's skewed. So since the tail is on the right, we say that this is skewed to the right. Okay, if it were the other way around, if the tail were on this side, okay, we would say that that particular type is skewed to the left.